a heavy steel rod thrusts downward, forcing dense hydraulic oil against a rubber O-ring under immense, crushing mechanical pressure. Our everyday experience suggests that liquids cannot hold weight, as we expect water or oil to flow away from physical resistance. But trap that same fluid inside a sealed cylinder, and its physical behavior changes. It assumes the structural rigidity of solid steel. Early industrial engineers exploited this behavior to crush, bend, and shatter heavy materials with a force that seemed impossible for a liquid. For over a century, engineering shorthand has treated this trapped fluid as an incompressible, solid rod, transferring kinetic energy from one end to the other. Yet treating it as a solid rod ignores the underlying physics. What happens inside that dense fluid matrix when thousands of pounds of pressure bear down? Force travels through the fluid as an incredibly rapid chain reaction at the microscopic level. To understand why this system is so unyielding, we have to look past human-scale physics entirely. We must bypass the steel casing and plunge into the molecular architecture of the oil itself. The power of hydraulic machinery relies on multi-layered physical processes, extending down to the interactions of individual atoms. Industrial hydraulic fluids are primarily highly refined oils. Chemically, they are composed of thousands of long, complex hydrocarbon chains overlapping in a dense web. Under normal atmospheric pressure, these heavy molecules float loosely, continuously sliding past one another in a chaotic matrix. Solid metals, like iron or steel, maintain their shape because their atoms are locked into an immovable crystalline lattice. Fluid molecules have no such fixed architecture. Instead, these hydrocarbon chains are held together by van der Waals forces. These weak, elastic intermolecular attractions keep the liquid coherent without freezing it into a permanent shape. These weak bonds allow the individual chains to stretch, bend, and physically conform to the internal geometry of the steel container housing them. Because the molecules can physically rearrange themselves on demand, the fluid flows to fill any available void within the mechanical system. This state of molecular flexibility creates an adaptive structural medium, primed to receive and channel massive inputs of kinetic energy. When the primary piston strikes, it compresses the physical volume available to the fluid inside the sealed cylinder. The free space between the hydrocarbon chains collapses. Billions of complex molecules are forced into severe, inescapable proximity. At this scale, the boundaries of these molecules are defined by their electron clouds, dense fields of negatively charged particles orbiting the atomic nuclei. Forcing these outer electron clouds together triggers violent electromagnetic repulsion. The negatively charged fields fiercely repel without ever physically intersecting. Because the steel housing is completely enclosed, the molecules cannot escape this repulsion. The kinetic energy has no other path for dissipation. This inability of the electron clouds to overlap translates the mechanical push into a rapid, omnidirectional pressure wave throughout the entire fluid. The dense liquid acts as an unyielding physical wall because we are pushing against an invisible, continuous electromagnetic force field. Engineers scale the law of atomic repulsion to create hydraulic power, relying on the physical barrier of the electron cloud. This electromagnetic shockwave blasts through the fluid matrix at the speed of sound, striking every exposed surface, including the face of the secondary piston. The system follows Pascal's principle. Any pressure applied to a closed fluid system is transmitted equally and undiminished to all points within the matrix. Pressure equals the ratio of a physical force divided by the specific surface area it acts upon. An input force on a 1-by-1 grid generates uniform internal pressure. Following Pascal's principle, this identical pressure strikes the larger secondary piston, pushing every square unit of the expanded grid. Scaling the surface area multiplies the total resulting upward force. Through geometric expansion, a concentrated input at one end of the fluid matrix generates enough distributed upward thrust to hoist multi-ton loads. A hydraulic cylinder acts as a physical amplifier, using the incompressible fluid as a mathematical conduit to scale mechanical strength. Multiplying shear force appears to generate free energy, but the laws of thermodynamics forbid creating energy from nothing. The law of energy conservation dictates that whatever the mechanism gains in load capacity, it must pay for elsewhere. To achieve this massive spike in output force, the initial input side must travel an extended distance to displace the necessary fluid volume. Additionally, the system faces an internal penalty, known as viscosity, the friction of thousands of hydrocarbon chains tearing past one another. This molecular friction cannibalizes a portion of the incoming mechanical energy, converting it directly into parasitic heat. Overheated fluid drives through narrow aluminum fins, shedding its thermodynamic load before the entire system reaches its breaking point. If cooling mechanisms do not remove this heat, the increasing kinetic energy will eventually overcome the intermolecular bonds, causing a catastrophic failure. The hydraulic amplifier operates within the boundaries of the universe, achieving power through geometric and thermodynamic concessions. Generating thousands of pounds of atomic repulsion provides the muscle, but that force is useless without control over its momentum. A mechanical valve redirects the fluid momentum, slicing through the high-pressure stream to throttle the continuous atomic force. By adjusting these physical gaps down to the micron, modern electronic sensors manipulate thousands of pounds of pressure with millimeter precision. Precision control maneuvers massive physical loads in real time, such as adjusting heavy aerodynamic control surfaces against wind resistance mid-flight. The valving network acts as a mechanical bridle, taming the turbulent atomic power of the fluid matrix into predictable physical outputs. By harnessing the behavior of trapped electron clouds, engineers laid the foundation for modern global industrialization. These systems handle heavy metallurgy, suspending and pouring tons of molten steel. Controlled fluid pressures drive turbine networks, generating electricity at a continental scale. Defense systems use them to rotate heavy armored turrets under continuous kinetic stress. Civil engineers scale these actuators to rip terrain apart for urban expansion, and assembly lines use identical hydraulic pressures to perfect mass production. Trapped molecular repulsion translates through the fluid matrix, driving heavy iron machinery to tear concrete slabs from the earth. By exploiting the limits of atomic structure, engineers turned the physics of electromagnetic resistance into the physical muscle of the modern world.